Okay, let's start, because time is precious. Start all my timers. Okay, well, thank you for coming. This is going to be a whirlwind talk, and you'll see why in a second. We're going to talk about JVMs and what's happening and why stuff is happening, and it's an interesting adventure for all of us who are in the JVM space. So I work for IBM. My name is Steve Paul. I'm a developer advocate, which means I get to come on and talk about the cool stuff that we're doing, and that's quite nice and exciting. I've been doing Java JVMs since, well, before they were one, a very long time, and it's been fun, and it's been a real evolution of Java over those years and seeing how it's changed. And now we're at a position where we're going to change again, and lots of things are happening. Now, I have to start with an apology. There are some things in the abstract for this talk that I'm not going to talk about because it turns out I have 35 minutes and something had to give. And so I'm not going to talk about development tools and what JVMs are doing in that space. I'm not talking about GPUs. So if that's what you came to hear, you want to leave now. Okay. What I'm going to do is focus on the specific driver that we're all aware of and what that means for JVMs, and then what is happening in the JVM space to address some of these challenges. Okay. So where do we start? Let's start with here. What does Java do? Java makes things go fast. Java is an application. We write Java stuff in Java, and our JVM makes that Java really fast. We have built, over the 20-odd years, this amazing space to run your Java code. Right? We have tuned a JVM to run enterprise Java very, very well. We've worked together for all this period of time to create what is undoubtedly the fastest runtimes, the most scalable runtimes. We have taken the problems that are hard, and the JVM community have fixed them. Right? We have the best garbage collectors. We have, within the JIT, the best recompilation technologies, reoptimization technologies. We have invested in this industry many, many, many millions of dollars in making this reality. It is the best place. The challenge is, though, that the innovation that drives us isn't something that tends to just magically happen. It's all driven by some outside force, right? You don't sit up one day and go, hey, let's make the JVM do this or this or this. That's not what happens. What happens is we live in a world and the world changes and we respond. And the latest thing that's been driving us is this thing, cloud. Yes, all about making things cheaper and easier. You know the blurb, okay? The challenge for us is this is the shape of Java performance. If you look at any of the benchmarks that get run, enterprise benchmarks, you will notice that they have a reasonable shape. You probably won't see the white line, but you definitely see something with the red line that says it takes time for your Java application to reach maximum throughput, which is the red line. It takes time, and along that journey, we probably use more memory, big bump of memory to get there. And that is an acceptable profile. And we'll talk about that in a second. But that profile is acceptable for the old way of doing things, traditional way of doing things, okay? It doesn't fit when we move it to the cloud. The reason it doesn't fit when we move it to the cloud because the economics are different. So there are two obvious economic differences. One is if you use more memory, you have to pay for it. So if you have big bumps of memory, you might find that you have to buy, say, the next tier of a VM on Amazon or whatever, just to get your application started, and then not use it again. That's not a good idea. And if you can't, the longer it takes your application to get going, maximum throughput, that costs money because who's dealing with the workload? You're just firing up a machine, it's got to do something. Where's the workload going to be handled in the meantime until this VM's ready? Well, you have another one running. So lag is a really horrible problem for us too now. Okay? We want this pattern. We want it to look like this. On, no bumps and bruises, just straight away working. Yeah? So we say we need, cloud says, less memory, small deployment sizes. That does save money in various ways, and fast starting applications. Yes, that's the sort of thing we're asking for. Now look, if I take some real data, and whatever benchmark you want, you get wiggly lines like this. Okay, so this is a real thing, and you go, okay, this is what it takes. It takes this long to get throughput, whatever the time period is, and you get these bumps and things. What's going on here is, the reason that the throughput is increasing is because your JIT kicks in and helps push it up. Your JIT is converting your bytecode to machine code, okay? The economics of the situation are this. We are spending time at the front of the application in terms of compilation to give you the maximum throughput. We have agreed that it's okay to do that. We have agreed that it's okay to take time to re-optimize because it pays off in the long run, because the application goes on forever. Okay? Now, if your application doesn't run that long, then all that investment in trying to optimize it for the future gets wasted. So you end up with this situation, you get less throughput than you expected because you haven't had time to profile the application, and we're all beginning to suffer. So, what are we doing? Two different workloads. Long-running things, large applications, you know the works, and then versus microservice, small containers in a container. Different thing entirely. Right. So I need to go back to basics before I talk about this, because this is actually a topic we could probably spend all day on. But I'm going to give you a really quick sheep dip so you can see how some of this works. Okay, so first things. Java, JVMs don't run Java. Everybody says they do, they don't. JVMs don't know much about Java. JVMs run bytecode, yes? Class files. That's what it looks like. JVMs don't actually like class files. Not that they have any emotion over it, but it's a problem for us because they're designed prior to the internet. They're designed for a common universal machine, stack-based machine, which is a problem for us because we have to re-engineer from a stack-based machine what a real machine would be doing. That's a problem for us. And of course, it's in this format that was designed to be as small as possible, pre-internet, no network access, runs on a toaster. So we don't like that. That's a problem. It costs us time to get things up and running. And out of the box, you have this bytecode, and you have to get going. So how do you go from nothing to something? Well, you tend to end up with something that would be called an interpreter in the original days, almost like a switch table. It's not quite that bad anymore because we have tiny JITs that can deal with this. But it's a problem to get going because you have to start one somewhere. So we have to fix that. So we fix that by having just-in-time compilers that take the bytecode that you've got in your class file and turn it into machine code targeted at the platform that you've got. Yes? We get that. That's what it's there for. Okay? However, when you look at the bits and pieces here, right, and this is quite abstract, you have bytecodes, you have things going on about threading and locking, you obviously have some garbage collection, and then you have this interpreter loop or whatever, and then you have all the runtime libraries, all the C code that does things for you, okay? JITs don't sit there and just go, hey, you can use us instead of the interpreter and produce machine code. That's what it does, but JITs do more than that. JITs inline, enhance, replace some of the critical parts of a VM. Okay? It doesn't just sit on the side, it does other things as well. So it has a real symbiotic relationship. And in fact, what the JIT does, it ends up generating machine code, which has that relationship. So at the end of the day, your machine code has a tighter relationship with the JVM than perhaps you realize. Okay? From a JIT point of view, C code is really heavyweight. You may not think about it, but C code has its own structure, has error handling, it has frames, there's all sorts of thumbs that look very much like Java code in one level. And it's there to make sure that if you do something stupid in C code, you don't hang your machine, or okay, it's there to protect you. We don't need that when we're generating our own code because we're in complete control of what's going on. So when the JIT calls back into C code, everything slows down, right? We don't like that. We don't want to call back into C code. We want to inline stuff as much as possible. Hence why JITs do some part, they'll have their own version of the GC code. They'll have the home version of some of the threading and the locking, and it'll all be the same semantics, but implemented in differently, okay? That's where we get the performance, not just from giving you an alternative to a compiler, but actually by this integration, okay? Everything that we can replace with machine code will make your application go faster. Okay, right? Now, JVMs have this good-bad thing. It was always been good, now it's not necessarily so good, is that it's dynamic. You can load code after your application started and it just falls in. Yes, we're all quite used to doing that. So JVMs have to be cognizant of whatever they do, things may change. Right? Your Java application has to be flexible because what you're running could change. You can use reflection, all those sorts of things, okay? So we can't actually guarantee that we know what your application is going to do and give you a full optimization. We couldn't step out completely and say, we've machine generated everything you need, there you are, right? We can't do that because A, we don't know how much code you're actually going to load until you load it, right? And the other thing here is we have to run the machine because the other value that you're getting is optimization against what you really do, not against what the code says it should do, right? You write your code, any other path can be taken. The JIT will learn what path actually gets taken and optimizes for that, okay? Which I think I just said there, yeah, okay. So back to this thing. How are we going to deal with these conflicting things? So, JVM people put a lot of thought into this, and there's all sorts of things that we could do. Nothing of this is particularly novel. We've had the idea for a long time, but you can break them down to a bunch of stuff, and we're going to talk them through. So JIT differently, of course. Let's have a different think about how we JIT and when we JIT and what we JIT. Maybe if we replace some of the C code with Java code, we could get a different relationship. So maybe some of the native code become Java. That could be JITted. There's some trade-offs, okay? Obviously, retune. GC and JIT they're heuristically driven. We can change the heuristics to match the new workloads. Maybe spend some time not wasting memory. That would be cool. And thinking more about how we share stuff, because if we share things that we've created effectively, then we don't have to keep repeating stuff. If you think about it, large application servers have had the luxury of running around forever, and you were willing just to keep restarting them, and so it was no big deal. But if we can share stuff that you created from a previous time, we can help you get started. Oh, and by the way, we should add some container awareness because, we weren't very good at that to start off with. That's not particularly rocket science. That just needed to get in there. What that meant was we were ignoring the fact that JVMs are running inside containers, and we were talking straight down to the low levels and being convinced that we had more memory or more CPUs than the Docker container was telling us and those sorts of things. Okay. So then there's an AOT versus JIT story. So one of the things you can say, of course, is let's compile stuff and save it, and then we'll just pick it up later. Right? And I said part of the problem we have with that is that we don't know what your application is going to do until you've run it. So actually a lot of AOT isn't actually AOT in the real sense. It's actually load it once, run it once, save it, and use it again. But you can see there's a bunch of trade-offs, and they're the obvious trade-offs. If you AOT stuff too early, if you compile things too early, you won't necessarily get some of the speculative optimizations that we can apply by knowing more about what your application is going to do, versus, well, if you've already compiled it once, we don't have to do it again, so we can save memory and CPU, okay? So all these wonderful trade-offs. However, the big one for us, the big challenge for the future is this one. It's the dynamism of the JVM. It's the dynamic loading. It's the fact that you've got reflection, the fact that you would expect reflection to work and be able to get in and do things. They get in the way because if you think about what actually happening here is that when you convert things to machine code, we are opting out of the Java world, right? We're trying to create an application that runs on your platform, and it started off looking like Java, but it's not anymore. So everything that's Java-like that you drag with you gets in the way. Okay, so there, I'm halfway through, and I haven't said anything other than possibly what you already know. So I'm going to give you a quick whirlwind through what's going on. We're going to look at these 4 things, 3 of which you may know, the 4th one you may not. Okay, so let's start with Hotspot. Who's using Hotspot? Everybody uses Hotspot? Yes. Okay. So there's some stuff. I'm not going to read them out too much, but you know. So we've got container awareness coming in. We've got class library sharing coming in. If we can put some of the metadata that's in those class files on the disk in a better structure than what we had before, not a class file format, because basically that sucks, a better format that we can reload, that will save time. We can share that. We can bake those into Docker images. That makes startup just that bit faster. That's good. And yes, we have better awareness of Docker, which I said is sort of like, well, we should have done that early. What else have we got? Well, Java 9 brought us an IoT compiler called Graal, which we'll talk about later. A new thinking about trying to compile our Java code into machine code. That's really good. And then 10, we got Graal as a JIT, so reimagining the JIT, and we'll talk about Graal later. And then a sort of, I always thought it should be an April the 1st thing, which was let's have a GC that doesn't do anything. But actually, for a bunch of applications, you may go, actually, why would I spend all the time trying to build into the architecture of the application I'm creating all of the sync pointing I have to do GC? That can be a waste. If I can show that I don't actually need to do it and I'm just going to run within a certain amount of memory, I'm not going to run out of memory before my application completes, that might be a reasonable thing to do. So it's a good thing to put on the list to play with. Okay. And then there's J9. Anybody here using OpenJ9? Ooh, anybody here using OpenJ9 who doesn't work for IBM? Hey, look at that. Okay. So this is an Eclipse project. We open sourced this in 2017, contributes to OpenJ9. You can go read all about it. Let's talk about what it gives you. So OpenJ9 was slightly late to the party in getting a good shared classes story in terms of playing well with Docker, but that's fixed. What J9 gives you that Hotspot doesn't give you is that you can share code. Hotspot lets you share the metadata. J9 goes further and says that JIT code that you've created, we can cache it in the same place. We can bake that in the image. So we can run effective AOT, run it once, capture the data, put it in a cache, bake it into your Docker image, get things running much faster. J9 also has some memory improvements, which are just there almost historically about giving you literally halving the memory costs. And it really pretty much is just switch and you'll see. And that's because of where it started and what it's required, what it was designed to do originally. They've always been very, very careful about where memory gets used. So you get that. So that's just out of the box, and container awareness out of the box, etc. So J9 says, you know that picture I started off with, that benchmark? So there's the Hotspot version. There's the switch to J9. You get that performance profile just switching to a JVM. Changing your JVM can give you immense benefits because it comes from different thought processes, different spaces. So that's just a switch. If you turn on the AOT, so run it, capture it, rerun it, well, we haven't quite got the throughput yet, but it's getting close to that profile that we were looking for. That's a good sign. Okay, J9 also comes with this thing called jitter to service, which you may have heard about. This starts from a different point of view. This is us exploring what happens if you don't JIT at all? What happens if you take the JIT code and don't JIT it in your application, but JIT it somewhere else in a long-running service? So your microservices can live and die at their normal space, but you have somewhere else which is creating that caching code. So you have no JITs here in all your clients, but you have a central server or multiple servers that's doing the heavy lifting. They get to see your application over longer periods of time. They can do better optimization. The next time you connect to it, your next thin client gets the benefits of all the others. Right? Now, it's still early days on this stuff. The most immediate thing is your memory footprint spikes. Those things you get disappear because you're not spending any money doing any JITting because you have no JIT. Right? But you still get, everything that you're back to that. And for in constrained environments where we limit it down to really small clients, it's really showing value in trying to get the throughput up. Because in constrained clients, your client is in small amounts of memory, everything's fighting for itself to do the JITting and run your application. So by taking out the JIT from that environment, you mean all the CPU goes into running your application. Okay? And that can really improve throughput in those circumstances. So cool. So we've got Hotspot, OpenJ9. We've got this one. Anybody tried Graal? Anybody play with Graal? Okay, so cool. Another approach. Graal starts from a different place. Graal is looking at different problems. So it's looking at, let's write things in Java because if I write things in Java, it's easier. But it's also saying, can I mix in other programming languages? Can I have Java mixed in with Ruby or Rust or whatever they want to do and create this polyglot runtimes? Okay, and can we get really close to the native things? Can we create native applications out of Java? Graal is in that space. And I really encourage you to play with it and go read about it. However, Graal is also exploring, either deliberately or sort of accidentally, what happens if we don't follow the spec that we have said at the beginning was, well, it can make it harder to work out what's going on. So if you go to the Graal website, you'll see they've got currently a bunch of things that are chain challenges. Right? And now some of these are all reasonable things to have a look at and say, if we were going to do this differently, if we're going to give you the performance that you want, what has to give? And so Graal is looking at that space, right? And right now it's earlier days, so there's a whole bunch of stuff around reflection and things that are going to be interesting. But it's giving immediate benefits. So these are benchmarks from their website. So you've got 3 app servers frameworks that have been tuned. They have been set up so they will run on Graal. So a whole bunch of the challenges that we've talked about have been worked around, right? And you get good performance. You can run it in normal mode, which is the gray bar, or you can do you create the native image. You get massive reduction in memory footprint. Cool, right? And startup time, as everybody keeps saying, can be really good. Now, what we're not sure of yet, and this is still to play out, is how far that goes, and if you apply this to long-running applications or big scalable applications, are we going to hit problems? Don't know. But these are all good things to explore. Garand is making us think about how we think about Java. Right? The JVM guys are having a good look around this and going, what could we do? What could we do differently? We have talked for years about adjusting the spec, but we've never actually got together to actually make that happen. And Graal is making that, is sort of being a forcing function to us to say, how would you think about doing Java differently? Right? How do we get the performance that we all want with the least disruption? And if there is disruption, how well can we encourage that to be self-contained, the least impact? We want to be able to continue to run everybody's Java code, That may not end up being the answer. Don't know yet. Okay, so whirlwind. Now I have one more thing I want to talk to you about. This is the thing. Anybody heard of CRIU? Okay, so this has got nothing to do with Java. This is one of those different interesting technologies that has been around for a bit, but became more interesting as we got nearer to what cloud wants. So you run up your Docker container, you run your application, and at some point, at any point you want, you can take a snapshot of the running memory. It's a bit more clever than that, but you effectively take a snapshot of the running memory, and now you have a definition, an image of how your application was behaving at that point. So now you bake that image into that memory image back into your Docker container, and then the next time you start your Docker container, you can ask CRIU to reconstitute the memory. Now, it's not just a blanket copy of memory, because it has to do some interesting little fix-ups, do file handles and sockets and things like that, but your application can start quicker. It doesn't matter whether it's running in Java or anything else. You can just take whatever you've got in a container and you can just snapshot it and fire it up. So I have a video. Now I have 3 things here. Yes, I know it says Pet Clinic, and I know this is not a spring conference, but that's what I've got. There are 3. I'd like to show you a Graal version, but Graal and Pet Clinic Spring don't work well yet together. So that's what you've got. So what this video is going to show you is clearing everything. So it's going to create containers of those 3 applications. So it's going to take a Docker container. It's not starting them, it's just creating them. So they're all ready to go. And then it will kick them off and it will time them. And when they're finished, the Pet Clinic web page will turn up. So this is how long does it take to get to the point that you can see the front door. Okay. So let's run this, says he. Right, now, and here we go, and start them. You're waiting for it to end, aren't you? It's going to end. When's it going to end? When's it going to end? Ah! Okay. Wow. So the last 2, OpenJDK and Hotspot. Okay, Hotspot is just slightly behind J9. It's not enough to be any notice. And of course, you run this again, and you've got these 3 things. They're all starting at the same time. So there's a bit of contention, right? So I'm not going to say this is a big benchmark, because it doesn't really matter about that. You can see the difference, right? So that tells you how long it took just on this machine to do that, to go from nothing to an application running based on Java or anything I wanted. In this instance, it took just under 5 seconds. Right? That's pretty impressive. And that comes from using technologies that are completely left field. Oh, now the bottom number, the last row, is how much memory did that Docker container consume to get that to happen? So there is a trade-off. So you see 187 meg from the middle one. That's J9 in its standard form. And you can see I said about 50%. You can see the Hotspot one is a bit more than twice that. But that's just out of the box. That's just normal memory. OpenJDK CRIU costs you more because you need some more memory to reconstitute things. So that's the cost. The cost is your memory usage on the day goes up, and your Docker image gets a bit bigger. Right? But in practice, it's maybe worth it because of that benefits. Right. I don't want to do that again. Why have I got 2 versions? Go away. Okay. So where are we? That was a whirlwind tour, but there's a lot going on. we're exploring from these different points. We have Hotspot as a base. We have Hotspot with Graal as a base. We have Graal VM on its own. We have OpenJ9, and we have other technologies. It's quite an exciting space, and there's some really cool stuff there. The expectation is that what's going to happen is this is coalescing, and we're at the beginning of these conversations, so you have to watch the space. My expectation is that what ends up will be something in the middle, because one of the things that we will have to agree on is, what is it that you're willing to give up in your Java application in search of the performance that we think you need? We don't know what the answer is, but there's enough innovation, there's enough experimentation, and these are sort of the safe bets, the things that we've gone, yeah, we know how to do that, right? They've been bubbling around. Or we've always said we could do this. Let's see what happens. What I'm interested in is what else falls out of this as we start thinking about this differently. Things like CRIU is making us think differently. Maybe there's other stuff out there. So JVM game over? No. It's into a brand new phase. And that's it. Thank you. So I have 5 minutes of questions. Any questions? If you want to throw rocks, we'll do it later. Okay. I apologize for the whirlwind tour, but 35 minutes is skimming. But if you want more conversations, I'm here for the rest of the week. Come to the IBM booth, and if I'm not there, just tell them that you want to talk to me, and they'll find me. But otherwise, enjoy the rest of the conference. Thank you.